Today, we're diving into something really cool, the AI's problem-solving toolkit. We're going to pop the hood and see how an AI actually thinks.
So, have you ever wondered how an AI can find the perfect route through a busy city or dominate a game of chess or even solve a tricky Sudoku? Well, I can tell you it's not magic. It's actually a set of really powerful, structured strategies for, well, thinking. And we're going to break them down. So here's what we've got on tap. We're going to look at 4 fundamental tools that an AI uses. First, we'll start with the basics, the search for solutions. Then, we'll see what happens when we go beyond the perfect map. After that, it gets competitive as we look at how an AI plays to win. And finally, we'll wrap up by uncovering the awesome power of constraints.
All right, let's jump right in. First up, the search for solutions. This is really the absolute foundation of it all. It's all about finding a path from point A to point B.
So, at the heart of this, we have what's called a problem-solving agent. And honestly, the easiest way to think about this is your GPS, right? It has an initial state, that's you in your car, and a goal state, your destination. The agent's whole job is to find the sequence of actions, the right turns, that get you from here to there.
Okay, so there are basically 2 ways an AI can go about this search. First, there's what we call uninformed or blind search, and it's exactly what it sounds like. Imagine you're in a maze, in the dark, just trying every single path until you finally bump into the exit. Then there's informed search. This one's a lot smarter. It uses something called a heuristic. And don't let the word scare you, it's just a fancy term for a smart guess or a rule of thumb. It gives the AI a hunch about which paths are more promising.
Let's look at a quick comparison to really see the difference. On one hand, you've got something like breadth-first search. It's blind. Now it's guaranteed to find the shortest path, which is great, but the catch? It does it by checking everything. And that can get super slow. We're talking exponentially slow. But on the other hand, look at A-star search. This one's informed. It'll also find the best path, but it uses that clever heuristic to focus on the good routes first. And that makes it way more efficient most of the time.
Okay, so let's move on to tool number 2. See, everything we've talked about so far assumes a perfect world. A perfect map, every action goes exactly as planned. But let's be real. What happens when we step into the messy, unpredictable, real world? Because in the real world, things go wrong, right? Actions can fail. A robot's hand might slip. Our sensors can be off. You might think you're at one intersection, but you're actually a block over. So the big question is, what does an AI do when it's not 100% sure where it is, when it can only see a piece of the puzzle? Well, it uses this really cool concept called a belief state. And the best way to picture this is to think like a detective. Instead of knowing exactly who the culprit is, the detective has a list of suspects. The AI does the same thing. Instead of knowing its exact location, it keeps a list of all the places it might be. Then a new clue comes in, maybe a sensor says, I see a window on my left, and bam, the AI can cross off every possible location on its list that doesn't have a window there. And it handles all this uncertainty with a simple, constant cycle. First, it predicts. It thinks, okay, if I move forward, where could I possibly end up? And its list of possibilities might actually get bigger. Next, it observes. It uses its sensors to take a look at the real world. And finally, it updates. It takes that new observation and uses it to shrink its list of possibilities back down. It's this constant loop: predict, observe, update, just chipping away at the uncertainty. All right, time for a whole new kind of challenge. What happens when the world isn't just messy or uncertain? What if it's actively trying to beat you? Welcome to the world of games. Many of us remember this moment from 1997. IBM's supercomputer, Deep Blue, did what everyone thought was impossible. It beat Garry Kasparov, the reigning world chess champion. And this wasn't just about raw computing power. This was about an AI outthinking and out-strategizing one of the greatest human minds on the planet. So this whole area is called adversarial search. And you're already familiar with it. Just think of any game where you have an opponent. Chess, tic-tac-toe, you name it. If one person wins, the other person has to lose. They're called zero-sum games, and yeah, your goals are in total conflict. The classic algorithm for this is called minimax. Here's how it works. The AI pictures a giant tree of every possible move that could happen in the game. Then it works backward from the future. It plays out scenarios in its head, assuming 2 simple things. First, on its turn, we'll call it the max player, it's going to pick the move that leads to the best possible score for itself. But then, for the opponent's turn, the min player, it assumes the opponent is just as smart
and we'll always make the move that's worst for the AI, minimizing its score. But here's the thing. For a game like chess, that game tree is, well, it's bigger than the number of atoms in the universe, so there's no way to search the whole thing. That's where a brilliant trick called alpha-beta pruning comes in. Think of it as a super smart way to save time. It lets the AI prune or snip off entire branches of that tree without even looking at them. Basically, if it starts exploring a sequence of moves and realizes, hey, this is already worse than another option I've found, it just stops. It doesn't waste any more time on that obviously bad path. Okay, for our last tool in the toolkit today, we're going to shift gears completely. We're moving away from finding paths or winning games, and we're going to tackle a totally different kind of puzzle.
So let me ask you this. Imagine I give you a map of Australia in only 3 colors. The goal is to color in the whole map, but with one rule. No 2 regions that touch can have the same color. How would you even start? See, this isn't about a sequence of actions like a GPS route. It's about finding one single solution that follows all the rules.
What you're trying to solve is a classic constraint satisfaction problem, or CSP for short. And every CSP has 3 main parts. You've got your variables, in this case, the different regions of Australia. You've got your domain, that's the set of possible values, so our 3 colors. And finally, you've got your constraints. Those are the rules, like Western Australia and the Northern Territory can't be the same color. Now, here's where the real magic happens. It's called constraint propagation. Check this out. Let's say we decide to color South Australia blue. Instantly, a chain reaction kicks off. The system knows that none of its neighbors can be blue. So just like that, with one single decision, we've eliminated blue as an option for 5 other regions. Think about how much that cuts down on the stuff we have to check. It's an unbelievably powerful way to make a huge problem much, much smaller. And this isn't just for coloring maps, this is a huge deal. CSPs are basically the backbone for solving all sorts of massive real-world puzzles. Think about it. A factory scheduling its machines, a logistics company planning its delivery routes, even a university creating its class schedule. All of those are really just giant constraint satisfaction problems. So there you have it. That's our AI problem-solving toolkit. Let's do a quick recap. We started with search, which is all about finding a path when the world is predictable. Then we moved to complex search for when the world is messy and uncertain. After that, we got competitive with adversarial search to win against an opponent, and we wrapped up with constraint satisfaction for finding a solution that fits a complicated set of rules. These 4 tools, they're really the fundamental building blocks of what we call rational thought. And each one is incredibly powerful on its own. But the real magic, the stuff that's happening today, is when these tools are combined, when they evolve, and when they're layered with machine learning. So that leaves us with a final thought. It's not just about what these individual tools can do. It's about how they can combine to create the kind of complex, adaptive intelligence we're starting to see all around us. What comes next? Thanks for joining me.